Uh, what we're doing here today is electromagnetic induction. So I'm just going to write EM for electromagnetic and then induction. Okay, and we're going to first start off, this is kind of our broad topic, and we're going to first start off by talking about flux. All right, basically this is the amount, like the amount, I guess I should put that in quotes, the amount of field, and even maybe like field lines going through a surface. Okay, so it's the amount of field lines going through a surface. Just imagine if we had, like, say, some sort of loop, right? Like a nice loop like that, and then we had some sort of field passing through that loop, and what we wanted to do is count up how much of that field is going through that loop, and that would be our flux. The way I think about this is I think of it like a hula hoop. If you walk down to a river and you held a hula hoop in the river and you counted the amount of water flowing through the hula hoop, through the area of that hula hoop, and that would be essentially what we have here. And so there's a few things that would affect how much water was flowing through the hula hoop or how much field is going through our surface here. Because remember, I always said think of these fields like flowing water, and so this analogy I think works pretty well here. So you can imagine this is going to be affected by a few things. First off, it's going to be affected by how quickly this water is flowing. So how strong is the current, or how strong is the field? So it's affected by the strength of the field, which would be the amount of water flowing through it, how quickly the water is flowing. If the water is barely moving and not really flowing at all, then not a lot of it's going to go through it. But if it's a rushing, whitewater rapids, real fast flowing river type thing, then a lot more water is going to rush through that. The second thing it's going to be affected by is how big is the surface, or the area. How big is the surface? In other words, the area of the surface, So however big this surface here. So if this is a big loop, like a giant hula hoop, or if it's like a little key ring, that's going to affect it. There's going to be more water can go through the hula hoop, that's bigger, than can go through the keychain. All right, they're both loops, but one is smaller and less water would be able to go through it. And the same thing with a field. More field could go through a hula hoop, putting them in the same place, than through the key ring. And then the last thing is the orientation of the surface. Orientation of the surface. You can imagine if this was my loop, and this is kind of like my above view, if this is my loop is like that, then I'm going to get a little bit of flux. If I turn my loop so that it's right angles to the flow of the field or the flow of the river, then more water is going to be able to flow through my loop, right? You're almost looking like this. I'm trying to do like a top-down view where you kind of see a slight angle of this. So imagine this is like a circle that you're seeing from above or something, and this would be flowing through it, and you'd get more flowing through it. And if you took and turned it all the way so that it was parallel to the field, where it was like that, then none of the water would be flowing through it, right? They'd be flowing down the sides of the hula hoop, or down the sides of the ring, and the same thing in the field. None of the field would be passing through it, it'd be going down along the sides of it. So we have those three things that are going to affect it, how much it is. And all of this kind of stuff, this is what we're interested in, thinking about this. The idea of all this with these with the flowing waters, it fits for magnetic fields, for B fields. There it's true, and so we can write an equation out for actually calculating this based on these things. Obviously, some of the things are gonna, these things are gonna make it bigger. So our symbol we use for this is the capital psi, and not psi, capital phi, and it's flux. This is our flux equation, and it's going to be equal to, first off, the strength of the magnetic field times the area of the magnetic field. And then we not only want to do the strength of the magnetic field, but we want the magnetic field that's parallel to the direction of the surface. And this is where it gets a little tricky. The direction, surfaces have a direction. They have a direction because you find area by basically taking the cross product of two vectors. And two vectors like this, like a vector and another vector, like when we did this, when you do the cross product of these two vectors, what it tells you is the area of a parallelogram that they would define. If I took this vector and put it up here again and this vector and put it there, this makes it a parallelogram and it creates this area. And also if you take the cross product of these two vectors, it gives you a third vector, a pseudo vector, that would be pointed out of the screen. It would be pointed up in this case. It would be this one crossed into that one, and it would be pointed out. And so it's the area of this surface, and it also has a direction to it, and the direction's out. It's perpendicular to it. So when we look at the direction of these areas, we have to be careful here. So if we say this is the field, right? This is our field. We're not really doing the area between, that's our field. When we have our loop in here, here's our loop, the area of it is actually going to be pointed off like, kind of like this here, where it's going to go out perpendicular. Oops, that was really bad. It's going to be, let me get rid of that, sorry. I can do a better line than that. It's going to be perpendicular to that surface. So it's going to point, oops, it's going to point out this way, perpendicular to the surface. And that's the direction of the area. It's perpendicular to that surface, like that. And then what you want is the component of the magnetic field that's parallel to that. So what you need, let me draw another field line in here. So what we'd have is, if we did a line parallel to the field like this, that was terrible. I can't draw very well today, I apologize. Not that I draw that great on this thing anyway. But if this is our line that's parallel to the field, right? Not a field line, but just a line that's parallel to that field, then the angle between them is that angle right there. It's the angle between the field lines and the line perpendicular to the surface. And since that is the direction of the surface, then we're saying B has to be parallel to A. But if you want to think about it, if you don't want to think about the surface of this thing, if it's confusing you too much, I mean, down the line in physics and math you'll have to know it, but if it's confusing you too much at this point, just change this parallel to a perpendicular and do the field that's perpendicular to the surface. Like you could say, oh, this is my surface here, and so it has to be perpendicular to it. So you're taking this component of the magnetic field, so if this was our B field, we would want this component of it over here, the parallel to the surface component, or perpendicular to the surface, whichever you want to think of it. Mathematically, parallel to it, because this blue line is the surface there. So what you end up with in the equation that you're going to be given for this is phi equals BA cosine theta, because this would be theta and this would equal B cosine theta, would be that parallel component. So this is the equation you're going to get for calculating it right there. BA cosine theta, and again, you want the component that's pointed through the loop, not parallel to it. This component here, this would be the other component there, and this is pointed. If you take that direction right there, it's pointed along the surface and wouldn't be going through it. So that component we'd throw out. We don't want that. We want the one that's perpendicular to it or parallel to the vector that represents it. Okay? So that's pretty easy. Now, what happens if we have a loop that has a lot of turns to it? So instead of just doing, if you think about this, we bring a wire or something in and it makes one loop, right? We would say that the flux on this thing is, phi equals BA, and let's call this area 1. And so we could make that area bigger. Say it's in the same magnetic field, we can make a bigger loop, right? And we can call that A2, and this would be flux, I guess, 2 equals BA2. Same magnetic field, but a bigger loop. And the magnetic field in this case would have to be either going, into the screen or out of the screen if it was, if we could have it pointed out of the screen, but it has to be perpendicular to that loop. So that can affect it, and then the last thing that can affect it is something that is sometimes referred to as flux linkage. I'm going to move this down a little bit. Flux linkage, it's like a nice fancy term for something that's probably pretty obvious, and the idea is if you take and make multiple loops, like you loop it around a whole bunch, right? I don't know if that's the best drawing, but each one of these loops I did has an area A. And so if the magnetic field is going through this, what you'll have is the flux, it'll be the total flux, the flux through this will be the total flux through all the areas. So it's like BA plus BA plus BA plus however many loops there are, and that's just going to be what? Flux is just going to be number of loops times BA. Okay? So it's essentially just that, which ultimately leads to, I guess you could say, the flux total is just N times the flux of a single loop, if all the loops are the same size, right? If they're all the same size like this, like it's a coil, say you coiled a bunch of wire together like this, coil, then the flux through that would be the number of coils would be N of the single loop. It would just multiply it out by that. It's just the total, essentially it's just the total area of all this. B staying the same. You could factor that out, B times NA, if you want to look at it that way. And this would just be the total area of all the loops added up, and that'd be that. Okay, I think that's pretty much it for this video. Spend some time thinking about it. This is one of those subjects where it's very hard to draw and it's kind of hard to explain, but if you think about it, and I really think if you think about that hula hoop in the running river thing, and how can you turn the hula hoop so that no water flows through it versus the most water flows through it, and things like that, things that would affect it, it'll really help you a lot kind of with understanding what this flux is and how to maximize it and how to minimize it and all that kind of stuff and what affects it. All right, so I think that's it.